Hello everybody, Namaskar. In this lecture, we will discuss about essential oil and oleoresins. Okay. Here, we will discuss, we will study what are the essential oils and oleoresins, what are the extraction techniques, maybe conventional and novel extraction techniques, and we will also take a few case studies like extraction of clove oil, turmeric essential oil and lemongrass oil. So, what is essential oil? What is oleoresin? So, essential oil is a concentrated hydrophobic liquid containing volatile, which is easily evaporated at normal temperature. Okay? That is the volatile chemical compounds from the plants. They are also known as volatile oils, ethereal oils, ethereum are simply as the oil of the plants from which they were extracted, such as oil of clove, turmeric oil and so on. The oleoresin is a nature or artificial mixture of essential oils and resins. They are resin like semi-solid extract composed of essential oils or fatty acids or fatty oils. So, both essential oil and fatty oils are present in the resins. They are little bit thick than the essential oils. Okay. They have the pungency and aroma which contribute to the taste of the food product. So, that you can say that major difference between the essential oils and oleoresins, that essential oils normally they may not have the taste and flavor, they may not, but the oleoresin definitely they will have the characteristic taste and flavor of the particular commodity from which they are made. Okay. Here these are the some of the examples of essential oils and oleoresins in this table, like essential oils, that peppermint oil, eucalyptus oil, wild mint, van tulsi, lemon tulsi, clove oil, lemongrass, khus, citrella, their botanical name or family name is also given in this table. So, these are the some of the common categories of materials which are known for their essential oil content. Okay. That the oleoresins like black pepper oleoresin, capsicum oleoresin, cardamom, cassava bark, celery seed, mace, nutmeg, parsley, turmeric, cinnamon, all these are used for their oils are made with the oleoresins. So, active compounds in the spices I have summarized in this table, like in the turmeric you all know that is the curcumin is the major active compound. It has anti-inflammatory, anti-coagulant, or it is used for dental purposes, etc. Garlic has allicin, diethyl disulfide or diallyl trisulfide. Its anti-active compound of garlic is known for its antibacterial, antiviral, antifungal or anti-carcinogenic activities. In the ginger, there is gingerol, paradol or gingerone. These all compounds are known for their antibacterial, antifungal, antiviral activities, etc. NSA, the active compound is 1-methyl-4,1-propenyl benzene. In clove, it is the eugenol. In lemongrass, it is the nerol, citral, geraniol acetate, citronal, geraniol. In cardamom, it is 1,8-cinolone, terpinolone, mycin, quercetin, luteolin, or in cinnamon, it is procyanidin, cinnamaldehyde, etc. And all these active compounds which are present in different spices, they are known for their antibacterial, antioxidant, anti-hyperprotective, etc. that they have the medicinal properties. Okay. So, for the extraction of these essential oils and oleoresins, that is the different techniques are used, like you see spices, etc. That is you have seen in the earlier slides that they are hub of the various chemical compounds, bioactive compounds. So, using appropriate extraction technologies like conventional method hydrodistillation, steam distillation, solvent extraction or maceration, whereas the novel technique like supercritical fluid extraction, subcritical extraction, ultrasound assisted extraction, microwave assisted or pulse electric field assisted extraction technology is used. Then these extracts, aisles or oleoresins are obtained, and they are then subjected to various food applications to add functional properties into the food, improve food safety, because many of them has antimicrobial activities, or also they are used to enhance food colors like curcumin, etc. They are known as natural colorant. Many bioactives which are present in the spices, etc. They give good natural food colors. So, these essential oils or oleoresins are used in food for various functional applications. Okay. Now, let us see some major methods of the techniques for extraction. First, we will discuss conventional techniques. In this, hydrodistillation is one common method. This method consists of immersing the plant material, as you can see here in this figure. Okay. Here that the plant material is taken in a water bath, and the mixture is then heated to boiling point at the atmospheric pressure. Under a source of heating, the odorous molecules which are contained in the plant cell, they are released in the form of an azeotropic mixture. Okay. Although most of these components have boiling point above 100 degrees Celsius, but they are mechanically driven with the water vapor. The cooling by condensation leads to separation of the mixture water and the essential oils by decantation. You can see here it goes, then come in the vapor, and then a condensation system is used where this you see in the separated, that is aromatic water, and the essential oils are separated. The water and the volatile molecules, that is essential oils, are separated by their differences in the density. The duration, generally it may take around 3 to 6 hours. Then steam distillation is a suitable to extract heat sensitive component or volatiles and purify them by the application of steam. Here you see here that in the figure it is almost similar, but here that hot water, it is boiling water or steam is used. Okay. The extraction of the desirable components at a temperature below their boiling point and the application of steam would volatilize them at a temperature lower than 100 degrees Celsius at atmospheric pressure. The steam destroys the structure of the plant cells, it releases the contained molecule and takes away most of the volatile components. The oil is then carried by the steam out of the column into a cooling system condenser, where the steam is condensed into a mixture of water and oil liquid. Then solvent extraction. I hope you know the Soxhlet apparatus. This is the picture of the Soxhlet apparatus. Okay. And this involves dissolving the plant material that contain essential oils in a solvent and then evaporating it to the recover the essential oil. Solvent normally used are hexane. So, what is done here, that is a porous thimble is loaded with the solid sample, is placed inside the main chamber of the Soxhlet extractor. Then by refluxing the solvent through the thimble using a condenser and a siphon side arm, the extraction cycle is repeated many times. The extraction technique has also been combined with the microwave assisted extraction and ultrasonic assisted extraction in an attempt to improve the extraction of efficiency. That is, this solvent extraction can be used in combination with microwave assisted or ultrasound, where extraction efficiency is increased manifold. Then another conventional technique is the maceration extraction techniques. This technique is used for the extraction of essential oils and active compounds since old times. Okay. The whole or coarsely powdered crude material undergoes a grinding to increase the surface area for proper mixing of the powder material with the solvent, and then this process is done in a closed vessel where an appropriate solvent is added. The solvent is strained off, followed by pressing the solid residue of the extraction process known as mark to recover an optimum amount of occluded solution. Both the obtained pressed out liquid and the strained solvent are mixed together and separated from unwanted materials by filtration. So, agitation during maceration facilitates diffusion, separation of concentrated solution from the sample surface, and it increases the extraction yield. Here in this table, I have just given a comparison, that is advantages and limitations of conventional extraction techniques, that is hydro or steam distillation. Here it does not use any organic solvent, so it is advantageous. There is no need for the dehydration of the sample and it has a shorter extraction time. However, here the high temperature limits the use of heat sensitive phenolic compounds. In the solvent extraction, it uses both a solid sample with a limited solubility, and it is most simple and easy to use. However, it takes a long extraction time and the consumption of large amount of solvent is a limitation. Then in the case of maceration extraction, it requires a small volume of ministrum, that is the advantage, but the limitation is longer extraction time, poor solvent penetration compared to others, and also here the yield is low. We will now discuss the novel techniques for extraction of essential oil and oleoresins, and among them one of the very important technology which is used presently by many industries is the supercritical fluid extraction. So, here raw material is placed in an extraction container, which you see here extraction column, okay, where pressurize the fluid and regulate the temperature conditions, fluid carbon dioxide temperature condition, and then the compounds are in the extraction column. It is mixed with the basically the pressurized carbon dioxide, and temperature and pressure are controlled, regulated to the desired level, and here the compounds are dissolved in the fluid, they are conveyed to the separator, the compounds are collected at the bottom and the fluid is rather rejected or released to the environment. This is a step involved in the supercritical fluid extraction. Okay. And the critical point, that is for the, there is a critical temperature and critical pressure, and above which there is these liquids, carbon dioxide, water, or they behave as a supercritical fluid. So, it can easily diffuse under those conditions, it can easily diffuse into a solid matrix like gas, while also having a high capacity to dissolve compounds like liquids. So, supercritical fluids have both the properties of a liquid as well as gas advantageous. You can see here the critical point. So, for carbon dioxide, the critical point, that is critical temperature is around 31.1 degrees Celsius, and the pressure, critical pressure is about 72.9 bar, that is above which the carbon dioxide will be in a supercritical fluid states. Okay. So, these supercritical fluids have an advantage in terms of diffusibility, solute capacity, and low viscosity over the other solvents. Due to its low polarity, the solvation power of the supercritical carbon dioxide to dissolve the bioactive from a solid matrix get reduced. Thus, it is often used in conjunction with co-solvent or a modifier. So, many times that is the depending upon the nature of the compound which we are extracting, that the co-solvent or internals, generally ethyl alcohol etc., or ethanol etc., are used. So, selective extraction of bioactive compound or co-precipitation of heat sensitive antioxidant can be done using that super SCF as well as a mixture of SCF or internal or co-solvent. So, by micronization through supercritical anti-solvent SAS process, where supercritical carbon dioxide is used as an anti-solvent. So, the solute containing bioactive compounds are dissolved in an organic solvent. Carbon dioxide continuously flows into the extraction system under a regulated pressure and temperature condition. The solute organic solvent mixture is then sprayed into supercritical carbon dioxide, where the organic solvent is extracted out of the aromatized solute droplet by carbon dioxide. Results, and this here due to high immiscibility of organic solvent, that is supercritical carbon dioxide at its supercritical conditions, and instant mutual diffusion occurs at the interface of the solute and the SC super, that is CO2, and this phenomena induces saturation and pulse separation of the solute in the supercritical carbon dioxide, and this finally results in the nucleation and precipitation of the target bioactive compounds. So, by using this, you can have even selective extraction of bioactive compound. Then subcritical water extraction. Again, this also on the similar principle, but here rather than carbon dioxide, that is the water is used and subcritical. The basic principle of extraction by this technique involves heating water to a temperature between 100 to 320 degrees Celsius at a pressure of about 20 to 150 bar. At these given conditions, water remains in the liquid state. However, the dielectric constant of water is altered, that is it is 80 at room temperature and around 27 at 250 degrees Celsius. So, the dielectric constant of water becomes comparable to that of the methanol and ethanol, which are 33 and 24 respectively at 25 degrees Celsius. So, due to the low dielectric constant of water, the polarity, viscosity and surface tension is reduced, and consequently the dissolution of the nonpolar molecules is improved, and one can get extracted these bioactive compounds, etc. The schematic of the whole process is shown here in this figure. Then ultrasound assisted extraction. Here the ultrasound having frequency ranges from 20 kilohertz to 100 kilohertz is used for effective extraction of functional compounds. Okay. That when ultrasound is applied, you can see here in the figure, there is a material there, ultrasound, then it causes acoustic cavitation. Acoustic cavitation results in a cell wall destruction, and that facilitates extraction. The propagation of ultrasound wave in liquid media induces cavitation bubbles to grow and collapse, generating various physical effects that includes microjets, shock waves and turbulence. These physical forces cause cell wall breakdown, cell surface holes and exudation of nutrients from the cellular plant matter into the solvent. Okay. The means that cavities, you can see here in this figure, cavities they are dependent on the number of acoustic cycles, etc. And then there is a expansion during the negative pressure cycle or contraction during the positive pressure cycle. Okay. The expansion and contraction is followed by the diffusion of vapor in and out of the bubble. A diffusion process causes accumulation of mass in the bubble over time, resulting in the net bubble growth, which is known as rectified diffusion. So, bubbles collapse after growing up at a certain size, that is called as resonance or critical size, and that is inversely related to the applied frequency. So, mostly water is preferred, but other solvents like ethanol, methanol, hexane, etc. can also be used in the ultrasound assisted extraction. Then microwave assisted extraction. You can see here in the figure, that is in a microwave oven, that some container is there where this the flask in the sample is kept, okay, and the heating system is through the microwave. So, it can be employed in combination, the microwave can be employed in combination with classical solvent extraction. So, microwave energy is absorbed by the polar materials. We have studied earlier also this effect, and is transferred into heat by ionic conduction and dipole rotation, which is known as dielectric heating. The solvent with high dielectric constant is selected for extraction of bioactive from spices and condiments, and for maximum absorption of microwave waves that converts into kinetic energy. The molecules with high kinetic energy thus diffuse into the materials, resulting in effective mass transfer of solute into the solvent. So, the factors which are need to be controlled during this microwave assisted extraction process are the sources of the raw material, its characteristics, etc., then permeability of the matrix and targeted compounds, which compound we want to extract here. Then accordingly, the microwave and other process parameters should be collected, should be regulated, used. So, the mechanism of microwave assisted extraction, that is the selective absorption of microwave energy by the water glands inside in the sample matrix. You can see here, and this waveguide is used. Then there is a localized heating above or near boiling point of the water, causing expansion and rupture of cell walls by disrupting the interaction between solute and active sites of the matrix through splitting of hydrogen bonds, van der Waals forces and dipole attraction. You can see here. Okay. Then disrupted cell promotes mass transfer of the solvent into the sample matrix and bioactive compound into the solvent. And finally, the extracted bioactive compound dissolve into the surrounding solvent, that see here in this fourth, that solubilization of the bioactive compound in the solvent. That is, first the solid matrix containing the extraction compound here in first figure, then you see disruption of the extraction compound wall, which is followed by diffusion of the solvent into the solid matrix, and finally solubilization of the bioactive compound into the solvent. So, this is the mechanism of microwave assisted extraction. Okay. Then similarly, the pulse electric effect extraction, PEF assisted extraction, that is PEF is a non-thermal method which includes cell destruction through application of electric pulses. Electric pulses are applied in short duration ranging from milli to nanoseconds at moderate electric field strength. The sample matrix exposed to electric field accumulate charges on either side of the molecule surface, generating transmembrane potential on the cell surface. When the transmembrane potential exceeds a certain critical limit, the weaker sections of the cell membrane creates pores which are known as cell electroporation. You can see in the figure, these are shown schematically. So, this cell electroporation promotes the increase in permeation across the cell membrane, facilitating the release of intercellular compounds. The factor which are responsible or which have the significant effect on this process include pulse number, electrical field strength, treatment temperature, specific energy input, and electrode gap. Here a comparison between the different novel extraction techniques is made, that is advantage and limitations. Supercritical fluid extraction, it is non-toxic, non-explosive. Here there is a better extraction of non-polar components, it results in partial extraction of partially polar compounds also. It has high solubility of oxygenated organic compounds of medium molecular weight. However, there is the limitation is the slow extraction kinetics. Subcritical water extraction, it is an environment friendly technology. There is low toxicity extraction method, it is. So, this is advantageous. However, the limitations are it is corrosive, maybe to equipment, etc., the temperature which is used here, and the high reactivity of the water at subcritical state. Okay. That ultrasound assisted extraction, it is shorter time, increased extraction rate, higher yield, but limitations are longer extraction time causes undesirable changes. Microwave assisted extraction, its advantage is it is a high extraction rate, less usage of solvents and shorter extraction time, but the limitations include solute degradation at high temperature and risk of explosion due to high pressure. The PF assisted extraction is a non-thermal treatment, it better selectivity, it preserves sensitive compounds and there are increased extraction yield. However, the limitations of this system includes this process, that is membrane changes can be reversible and air bubbles make the process less effective. Okay. Now, we will take up some case study. Here the case study 1 is the extraction of clove oil. So, you can see the characteristics of clove oil extracted from different parts of the clove plant. That is, these are the compound like essential oil, that is from bud as well as stem and leaf. That is the how much it is obtained in the bud, 18%, range is 15 to 20. That is from the stem, it contains, it is extracted is 6%, range may be 5 to 10, and from the leaf it is 3 to 4, the range may be 1 to 4. And their specific gravity, refractive index, optical rotation, total eugenol content, solubility in ethanol, okay, true eugenol acetate or beta cryptophyllate, all these their properties. They are these compounds from the bud, from the stem and the leaf, that is they are extracted and their characteristics you can see here. Okay. In this process, that is the comprehensive comparison of the clove oil. It is obtained by different methods. Methods used are supercritical fluid extraction, okay, that is using at 50 degrees Celsius and 10 megapascal pressure, hydrodistillation for 4 to 6 hours, steam distillation for 8 to 10 hours at 60 degrees Celsius, and succinate extraction with absolute ethanol for about 6 hours. Okay. And here in the succinate extracts were concentrated using rotary vacuum evaporator at 50 degrees Celsius. So, you can see here in these methods the yield, although yield is reported maximum in the case of succinate extraction apparatus, that is 41.8%, where it is followed by 19.6% supercritical fluid extraction, and then hydrodistillation or steam distillation almost similar. But if you look at the eugenol plus eugenol acetate, that is the active compound yield, it is maximum in the supercritical fluid extraction process and the steam distillation process, followed by hydrodistillation, and it is minimum in the succinate extraction process. Similarly, the extraction time is minimum in supercritical fluid extraction, okay, and it maximum is maybe steam distillation or succinate apparatus. The color and texture in the supercritical fluid extraction, you get pale yellow oil, the steam distillation also, but in the succinate extraction there is some discoloration, maybe brown and went. Okay. The organic solvent, obviously in the supercritical fluid extraction no organic solvent is used. In steam distillation, hydrodistillation and other 3 succinate extraction they are used. Here the extraction of clove oil, that is the eugenol content percent of the clove oil, extracts obtained at different extraction conditions, that is supercritical carbon dioxide 150 bar at 40 degree Celsius, 150 bar 60 degree Celsius, 185 bar 50 degree Celsius, 220 bar 40 degree Celsius, 220 bar 60 degree Celsius. So, different pressure and temperature combinations, supercritical carbon dioxide is used and succinate solvent, hexane solvent extraction. So, you can see here the eugenol content varies with the temperature and pressure both, okay, and you get maximum eugenol content in the supercritical, that more, that is in comparison to the succinate apparatus. Okay. This same thing you can see here, that is the yield of this at the time in the case of supercritical fluid extraction with the pressure and temperature is. So, you can 150 the 220 bar 40 degree Celsius temperature may be giving a better extraction. Then second case study is the extraction of lemongrass oil. This lemongrass raw material Levan gas pre-process, it is cleaning of the required part, large washing tank, it is fed, then feed to heating tank, steam distillation followed by oil separation and extraction, vacuum evaporation, then you get pure lemongrass oil, it is cooled at low temperature. So, the minimum citral oil yield of about 0.53% was obtained on sample particle size of 3 centimeter and bed volume of 80%. Maximum, and this was the minimum citral yield. The maximum yield of about 1.95% on the sample particle size of 50 centimeter and bed volume of 40%. Solubility of citral oil in the alcohol was around 70% in the ratio of 1:1 and citral oil concentration was around 79%. Here it is the extraction of turmeric essential oil, that is microwave assisted solvent extraction, the effect of microwave power and extraction time on essential oil yield during that when the solvent is the solvent extraction hexane solvent is used, and the other case it is the petroleum ether used as a solvent. So, in both the cases you can see from the surface diagram that RSM plot that extraction time significantly decreases from 30 to 10 minutes with the increase in the microwave power from 200 to 400 watt. Essential oil yield was higher when the hexane was used as a solvent in the case of A. Optimum condition for microwave assisted extraction was found to be 300 watt microwave power and 20-minute extraction time. The reference is given here. Okay. In this table I have tried to give you comparison of hydrodistilled oil to subcritically extracted turmeric oil. The compounds which are extracted as alpha curcumin, beta sequestrine, gingerberins, turmeric, urcurol. The hydrodistilled fresh turmeric quantity of components are also given here, and the subcritical oven dried turmeric, that is 25 degrees Celsius, 65 bar pressure, then quantity of component per gram is given here. So, in the subcritical oven dried turmeric, that is you are get no curcumin is obtained, alpha curcumin, in the hydrodistilled fresh curcumin, whereas in subcritical curcumin oven dried you get about 0.046 component per gram, that is okay, percent per gram. So, this is the table you can see, read the data. Then here again the average yield and percentage of key components as a function of pressure and temperature. Okay. In the extraction temperature, 3 extraction temperature are used, 25, 27 and 30, and each extraction temperature at least 3 pressures 65, 68 and 71 is obtained. Okay. And you can see that average yield on the dry weight basis are the percent key component determined in the extract. Okay. And with the bearing the both temperature and pressure, the yield percentage as well as extracted key components are changing. So, both the fresh peeled turmeric, fresh unpeeled turmeric, if you see dried peeled turmeric and dried unpeeled turmeric. So, obviously in both the cases the peeled turmeric gives the more volume of oil that is collected in ml in comparison to the unpeeled one, and the components in both this are given in this table, you can read. Okay. So, finally, I will say that yes, the demand for extracting bioactives by green technology with no solvent or minimal use of grass classified solvent is increasing. Okay. However, the selection of appropriate method, optimization of the extraction process techniques, etc., so that to have retain the extraction efficiency, retain the characteristic flavor and bioactive nature of the compound, etc. Okay. Owing to the potential toxicity of some organic solvents such as carbon dioxide, water and deep eutectic, etc., they give better efficiency. So, However, the more focus on non-thermal emergent technologies like PEF or combination of two or more technique like microwave assisted extraction or that PEF assisted extraction, ultrasound assisted extraction, they have better potential. They offer promise as far as the extraction of essential oils and oleoresins with good characteristic flavoring potential, etc., bioactive and antioxidant potential, they are promising. These are the references used in this lecture. Okay. Finally, thank you all very much. Thank you.